Let us see about magnetic field due to current carrying conductor. In the above activity, if we increase the current through the wire, the needle will deflect more, and if we move the compass away from the wire, the deflection in the needle will start decreasing. Thus, 1. Magnitude of the field produced at a given point is directly proportional to the magnitude of the current passing in the wire. 2. Magnetic field produced by a given current in the wire decreases as the distance from the wire increases. Right hand thumb rule. Imagine you are holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then the curled fingers around the conductor will give the direction of the magnetic field as shown. This is known as the right hand thumb rule. Let us do this activity. Take a rectangular cardboard with 2 holes. Take a coil of large number of turns. Insert the coil through the holes such that the turns are normal to the plane of the cardboard. Connect the 2 ends of the coil in series with a battery, a key and rheostat as shown. Sprinkle iron filings uniformly on the cardboard. Plug the key. Tap the cardboard gently. Observe. As the key is plugged, the iron filings form the concentric circles around the poles of the coil. Let us move to the next topic, magnetic field due to a current through a circular loop. It is seen that at every point of the loop, the lines are in the form of concentric circles, but these circles would become large as we move away from the wire. At the center of the loop, the areas of these circles would appear as straight lines. The magnetic field produced by a current-carrying wire at a given point depends directly on the current passing through it. Thus, if a coil has n turns, the field produced is n times larger than that produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Activity. Wind the insulated wire tightly around the nail in the form of coil. Connect the free ends of the wire to 2 terminals of the cell for few seconds. Bring small iron pins near the tip of the nail and observe. Disconnect the wire ends and observe. Even after disconnecting the wire ends, pins get attracted towards the tip of the nail. Repeat the above steps again. What do you conclude? We can see that the nail is acting as a magnet here which attracts the iron objects towards it. Magnetic field due to current in a solenoid. A coil of many turns of insulated copper wire wrapped in the shape of a cylinder is called a solenoid. The magnetic field lines in a solenoid through which current is passed are shown here. These lines are similar to that of the lines of a bar magnet. One end of the coil acts as south pole and the other end as north pole. Thus, solenoid has all the properties of the field produced by a bar magnet. With the help of a solenoid, we can magnetize a piece of rod of a given material. If the rod is hard steel and if the magnetic field is strong enough, a permanent magnet can be produced. Permanent magnets are usually made of carbon steel, chromium steel, cobalt and tungsten steel, and some alloys. 2 such alloys which are used in industry are Niperimag and Alnico. Niperimag is an alloy of iron, nickel, aluminium and titanium. Alnico is aluminium, nickel, cobalt alloy of iron. Permanent magnet of such alloys are used in microphones, loudspeakers, electric clocks, and many other devices like ammeters, voltmeters, and speedometers, etc. Activity. Take a small aluminium rod AB. Suspend it horizontally by means of two connecting wires from a stand. Now place a strong horseshoe magnet in such a way that the rod is between the two poles with the field directed upwards. If a current is now passed through the rod from B to A, you will observe that the rod gets displaced. This displacement is caused by the force acting on the current-carrying rod. The magnet exerts a force on the rod directed towards the right, with the result that the rod will get deflected to the right. On reversing the current or interchanging the poles of the magnet, the direction of the rod will reverse. This indicates that there is a relationship among the direction of the current, the field, and the motion of the conductor.